see what we can do today. So he just asked me about, in section 5.3, there's this 35. It gives you this integral from -7 to 7, the square root of 49 minus x squared dx. And anyway, there it is. Now, right, what are the directions? So first of all, the directions are not to do it. And I'll just tell you that you can't do it. If you try, you don't know, there's no way to do this integral until you learn some techniques in chapter 8. So this is a preview of Cal 2. But they're not, in 5.3, they're not asking me how to do it, or to do it. Well, here's what they're asking me. Sketch the region whose area is given. And then it says they do want you to do it using geometry. So you're not going to do it doing an integral because you can't, this antiderivative is tricky. This antiderivative is tricky, so I can't do it. But they do want me to sketch the region, so maybe I should pick up my graphing calculator and type this into my graphing calculator or plot some points and see what it looks like. The truth is I happen to know what it looks like, so I don't need a graphing calculator. So maybe sometimes I mislead you because I got a graphing calculator in my head. But this is a semicircle of radius 7. This is a beautiful semicircle of radius 7. So if you typed in your graphing calculator, maybe you would see that. And so it looks like that. And then if that's what it looks like, then this is the area. You agree? Yeah. I mean, an integral is area under a curve down to the x-axis from -7 to 7. I mean, these bounds make sense. This is a good old, so it's a good old semicircle of radius 7. But again, I don't know, I'm sorry. There shouldn't be anything mysterious, and maybe I'm not teaching you anything. I'm suggesting you type this in your graphing calculator to see what it looks like. That's what I'm suggesting. If you don't do that, what do you do? You want to do it without a graphing calculator? Without a graphing calculator, your brain thinks like this. You think, wow, what the hell is that? And then you square both sides. And if you square both sides, you get this. Do you agree? And then you add the x squared over here, and you say, oh, that looks familiar. I remember in pre-calculus, this was a circle of radius 7, centered at the origin. But then when you solve for y and choose the positive square root and not the negative square root, then it's the upper semicircle. It's not the entire circle. So, like I said, I don't know. I can talk or I can teach you all kinds of stuff. But really, I think you should just type it in your graphing calculator and see what it looks like. It's a semicircle. So, what's the area? The area of a circle, everybody should know, is pi r squared. But since it's half a circle, it's divided in 2. And the radius is 7, so I can 49 pi over 2, I think. It's pretty cool. But that's what that problem was. So you got to watch out. In 5.3, they're not asking you really to integrate. They're asking you to sketch pictures of what the integral is and maybe use geometry to do the integral. They got some funny questions in 5.3 because they hadn't really taught me how to integrate everything yet. Yes, ma'am?
Yeah, if it was below the circle, you want us to put in that it's a negative, if they were doing the other part. Because I was getting confused about when I think you have to draw the pictures, I guess, to know if you have to use negative on these areas.
Right. Well, I'm trying to, right.
Number 51, you mean?
Yeah, there was some of that too. And
Number 51's a great little question. Would you like any help with that?
It's hard out. I got the rest of them.
Oh, cool. Yeah. Yeah, part F's probably hard.
Because when you do those, like parts that are under, you have to keep the negative.
Right.
I mean, I just want to make sure. Now,
Well,
when we start integrating, it takes care of it because of the net amount.
I guess, right. So, yeah, I'm not sure how to address her question. She's asking me about, you know, this comment I made, really, this idea that if we end up with area below the x-axis, an integral, I just want to say, an integral treats area below the x-axis as a negative quantity. So that should be my statement. And then you could argue with me and say, wait a minute, area is negative, blah, blah, blah. Okay, that's true. Area is usually a positive measured quantity. It's not negative, no. But let's just believe me when I say this. An integral treats area under the x-axis as negative. An integral, it'll come out as negative when you do a problem with area that's shaded below the x-axis. It will. So that's okay. I mean, so I'm not sure what to do here. I mean, I could integrate this function. Look at this. I could integrate this function from -2 to 0. Now, either I can do it, or I can. Let's see. What if I treated it like this question? So if I treated it like this question, the question would be, draw a picture of this area. Okay. So I can draw a picture of this area. First of all, I can graph this function. This is called y equals x. Y equals x looks like this. They want me to integrate from -2 to 0. So if I'm integrating from -2 to 0, there's -2, there's 0. So I'm kind of integrating from here to here. So I think I'm getting this area. You know, the area between the function and the x-axis, I guess. So I guess what I've done is, here's an integral, and here's a picture of what it might represent. And again, that's going to be a negative number. According to the integral, it's going to be a negative number. I mean, see, it's funny. There starts to be two questions here.
Yeah.
One question is, if I say, what's the area, I think you better give me a positive answer. If I say, what's the value of this integral, I think you better give me a negative answer.
Okay.
I understand how this can be a little confusing, but you need to, what's the question? And understand that integrals are allowed to be negative. If it represents area under the x-axis, it will be negative. So you can crank out the integral and watch the answer be negative. You can look at this picture and realize it's negative because your teacher told you it would be. But I don't know, are we confused?
Well, I just want to know, when I do it, if we're using the geometric, do we keep it? Do we have to draw the picture to know to put the negative?
Well, again, what you need is you need some good directions, and you need to try to follow whatever good directions they have.
Okay.
So if these directions were similar to 35, then what are the directions? Sketch the region whose area is given, okay? Then use a geometric formula to evaluate the integral. See, I believe in those exercises with those directions, all the areas will be positive. They won't try to confuse you.
They were. Yeah.
You know, I could do, area is 1/2 the base times the height. I think the base is 2, and I think the height is 2. I think this area is, when you multiply that, I think this area is 2. Now, I don't know. Again, there's two things I want to say. I think the area is 2. What's the value of this integral?
The value of the integral would be -2.
-2.
So it just depends.
So, to figure out the value of that integral, do you take the integral of x dx and then plug in -2?
Well, okay, so again, what we're doing is, we're in 5.3 and we're doing this funny thing that's confusing everybody. I can see it. Right. In 5.3, you don't know how to do integrals. So their suggestion was, but here's what what they want you to get to do in 5.3 is take integrals and draw pictures. Integrals are pictures of shaded areas. So they want you to get used to that in 5.3. But then but they haven't taught you how to do them, so you can't do them unless they say this little comment, use some geometry. You can do it with geometry. And so if they give you triangles and circles and rectangles and squares and trapezoids, you know, if they give you very nice shapes, you can use geometry to get the answer. So I sort of tried to do that. And then we just got this other little comment. Dude, if it's area below the x-axis, the integral treats it as negative.
Okay.
You know, maybe I should tell you the truth. You want me to tell you the truth?
Is it that displacement?
I mean, here's the truth. The truth is, we're finding area between two curves. You know, maybe that's not the way I presented this. I presented this as area under a curve down to the x-axis, right? Okay, here's the truth. This is the way Cal 2 kind of starts. Not really. Anyway, but they don't put this in Cal 1. It's up in Chapter 7, I think. It's area between two curves. That's what an integral really is. It's the area between two curves. Now, here's the funny thing. Here's the top curve. What's the name of this top curve? Y equals the square root of 49 minus x squared. What's the name of the bottom curve here? What's the name of this?
Y equals 0.
Y equals 0. So when I'm doing this integral, what I got is I got top curve minus bottom curve. I'm finding the area between two curves is what I'm doing. I got a top curve and I got a bottom curve. You never knew that before. Nobody told you that before. Because the bottom curve is always the x-axis. And so it's just a 0. So subtracting 0, I don't know. I didn't have to tell you that before. But watch how that works over here. See, here's the idea. If it's the area between two curves, what's the name of this curve right here? Y equals x. That's y equals x. What's the name of this curve right here? That's y equals 0. Now, if I'm setting up area, if I want my integral to be area, I would set up top curve minus bottom curve. It's the top curve minus the bottom curve. And so I would set this up differently than this. If I want it to be positive area, I would say top curve minus bottom curve. That would be 0 minus x. So that would be, I would be negating. Look what I'm introducing a negative sign by doing this, right? And therefore, it'll negate this answer, and it'll give me an answer of positive 2. Now. Did I just confuse you? I think when you're finding area, it's always the area between two curves, and it's top curve minus bottom curve. But for us Cal 1 students, when we first get started on this, the bottom curve is always 0. And then we say, oh, but area under the x-axis is negative. But the reason it's negative is because if I set up top curve minus bottom curve, I would put a 0 minus that function and it would negate it and make it positive. Now you're really confused. Maybe. Any other good questions? You were trying to ask me something sometime, but
She
It
said
was back
51.
in 5-1, the Grand Canyon question.
yes.
I couldn't, my T value kept coming up wrong.
Okay, let me see what happens. In the Grand Canyon question, it's 58. It's 1,800 meters deep. Oh, were you using meters? That's one thing they do to you.
Yeah.
They switched it to meters. Now, you know, we had this equation, negative 16t squared plus v naught t plus s naught. You guys know this. If we take the derivative, we get velocity. If we take the second derivative, we get acceleration, which is really just gravity. But this is all, with that 16 number here, we're doing feet per second. So
Theirs was the 9 point.
if we're in meters, it would be a negative 4.9 right
Yeah.
here. And the velocity would be negative 9.8 t plus v naught. You guys okay with that?
Mm-hmm.
And the acceleration would be negative 9.8. Is that okay with you? And that, by the way, that is gravity in meters per second. Okay, so the first thing I noticed is they gave me meters in question 58. And so I thought maybe that could have been her error. But anyway, now what? What's the question here? The Grand Canyon is 1,800 meters deep. A rock is dropped from the rim of above that point. Write the height of the rock as a function of time. I kind of did that. I think the height of the rock as a function of time is this. Let's fill in a couple details though. What was the initial velocity? What was the initial velocity?
0.
Oh, because you dropped the rock?
Right.
It was just a 0. So V naught is 0. And what was the initial height?
1,800.
That was the 1,800, I guess. The height of the Grand Canyon, I guess. Okay, so specifically for this specific problem, this is the height of this falling rock. This is the height of this falling rock, right? That was pretty easy. Dropped with an initial velocity of 0 from an initial height of 1,800. Write the height of the rock as a function of time. Good, we did good. How long will it take to hit the floor? So the floor is 0. All right. So anyway, right. This is algebra. You move the 1,800. You move. You just do a little algebra here. So I don't know what happened. Divide by 4.9. T squared is 1,800 divided by 4.9. Take the square root. Can you help me? Anybody? That should be the answer. There's nothing too tricky there. Set it equal to 0. I mean, you could have made a little algebra mistake, but this.
I'm sure I did.
Well, can you see it? Because it would have been right here somehow, I guess.
Yeah.
19.166.
That's the final answer.
Okay, that's, no. Then the book is wrong.
Well, that's possible. This is number 58,
58.
so were you able to look it
Yeah,
up?
well, that's what I got, and the book was saying it was 9.2, so they didn't print a 1.
Okay.
So, that's, I kept going back, and I kept working and working, I'm like something's wrong here.
Good. Something
So
was
good.
wrong.
That's why
You
I'm
were
right.
right. Something was wrong.
Yay!
Yay, that is always a good feeling. Hey, that doesn't happen too often with this book. It's a pretty darn good book. You must have been looking at a solutions manual or something, right? Or something. Anyway, they're usually pretty darn good, but there is 3 or 4 or 5 little things I've seen over the years. Yeah, there are mistakes. Yeah, there are.
Considering that 58 is an even number, the back of the book only has answers for odd numbers.
Yeah.
Right,
I
so she was looking
yeah.
at something else, some
Oh, okay.
solutions manual or something.
Yeah. Good.
It had an error, I guess. So cool. Yeah, there's not much to know. When does it hit the ground? Right. Anything else you want to talk about?
Do you have higher and lower sum on the curve?
I don't know.
Which next?
Higher and lower souls.
Oh,
Give me the.
I have a question.
Yeah.
Regarding so, if you want to figure out the value of something, right? You have like the upper sum and the lower sum, right? Alright, so you have to integrate what's inside the integrator, and then you plug it in,
Right.
right? And then after that you plug both of them in. So what do you do with those two values? Do you subtract it?
Right. Now here, if you want to integrate this, we can do this. You ready?
No, it's integral.
He's just asking about doing an integral. And listen, what we call this are bounds, actually, just to get the proper word right. This is a lower bound and an upper bound. We call them the boundaries of the integral, the lower and upper bound. Really, it's their x values. I mean, visually, again, one more time, visually, this is a function called x squared. We all know what that looks like. I'm integrating from 0 to 2. Really, it's a left and a right bound. I mean, we call it upper and lower on this integral, but it's left and right because they're x values. So it's the left bound of 0 and the right bound of 2. And we're finding the area under this curve from 0 to 2. I mean, you're finding the area under this parabola from 0 to 2. I mean, you should get good at that. I mean, when you see that, your brain sees this maybe. But you know. But anyway, how do you do it is sort of what he was asking me. You do the antiderivative, 1/3 x cubed. You evaluate it from 0 to 2. Again, it's called eval. It's just this little, I make this little mark that says I'm going to evaluate this from 0 to 2. And what that means is plug in the 2. So it's 1/3 times 2 cubed minus plug in the 0. 1/3 0 cubed. So in the end, this turns into a number. I mean, in the end, when you first do the antiderivative, it's a function, but when you plug in the numbers, the answer is a number. And what does that number represent? The area under the curve, right? It does. It does. Most times. Anyway, this is 8/3 is what this is. That's 8/3 minus 0.
So how would I know if they're asking for area or value? Like.
All right. So sometimes I throw problems up here and do problems, and I don't necessarily do a good job of giving you directions, right? So what were the directions here? One of the directions could have been do this integral.
Right.
Okay, so do this integral. So do this integral. Another part of the question could have been sketch a picture. You know, sketch a picture of the region described by this integral. Of the region described by this integral. So there's a picture of it. That's a good question.
Right.
Here's an integral. Here's a picture. Here's the value of the integral. It turns out the value of the integral is the area under the curve. That's true.
If the value is negative, then it's not the area. It'd just be the
I don't know. You'd have to look at the picture to decide. It might be right. If the value is negative, then it might represent some area that's below the x-axis, maybe. Anything else? So, let me say something else. You know, so in 5.5, we learned about U-Substitution. And it's a process to help you do a lot of integrals you can't do. So look, here's a real baby one. So this is a very basic, very easy U-Substitution problem. And then look at this one. Here's a much more advanced U-Substitution problem. Let me see here. I don't know. That's sort of more advanced. And here's one that's a little more advanced. Yeah, watch this one. So these are all these are good integrals, but they're all starting in 5.5. These aren't on today's quiz, but starting in 5.5, these are good U-Substitution integrals. And that last one's real good. And this one is sort of, well, never mind. So do you know what to do? Can I help you? Can you help me? Do you know how to do U-Substitution and do this integral? What do you know what to do? What should I let U equal?
3x.
You think I should let U equal 3x? I agree. And now, when you decide what you're going to let U equal, you have to immediately find du, which means you're doing a little derivative right here in the middle of an integral. You do this little derivative move right here. I mean, this U-Substitution is you establish a relationship between u and x. And then from that, you have a relationship between du and dx. And you need those relationships so you can substitute it all back in and get yourself a form you know how to do. That's the game. It's kind of about fitting these forms. So you have a relationship between u and x. Now you need the derivative. The derivative of u is du. The derivative over here is 3 dx. And so you have these relationships established. This is not, some people think I'm making stuff up here. I'm not making anything up. I've established these relationships, and now I do this substitution. And watch how I substitute all this stuff, and this integral is going to look different when I substitute it. What's it going to be? I'll pull the 7 out if you don't mind. I have the sine of what? The sine of u. Thank you very much. And then the dx has to be replaced. So what is dx?
1/3 du.
Thank you very much. We spent some time Friday working on this. I appreciate your remembering some of it. Good. You divide by 3. 1/3 du is dx. I replace that. That dx gets replaced by what it is. I put the du here. I could put 1/3 du, but I like to pull the 1/3 on out. So this integral has turned into this integral. Look at it. It looks different, right? The main thing is the x's turned into u's. The result of all those x's turning into u's was it spit out a 1/3 out front somehow. But it's not somehow. This is how. This is why. Okay. So now you have to do this integral. All right. Anybody know what the integral of sine u is? It's negative cos u. Yeah, good. And we're done. Because it's a rule. See, what we're doing is we're fitting some rule. This didn't really fit any rule. This fits the rule. And so it's negative cos u. There's a 7/3 out front. So if you don't mind, negative 7/3 cosine of u. But I'm not even going to write u. What was u? 3x.
Plus
So, I don't know, that's classic, kind of basic, very basic baby U-substitution. All right, let's step it up a notch. I think this is stepped up a notch a little bit. It's really kind of the same thing. What would you call U on this one?
17 plus 2.
The denominator. You want to call U the denominator. I agree. I agree. Du then is the derivative. First thing I do is try to find du. 17 goes away. The derivative is 6x squared dx. All right. So now I start replacing stuff. You can do it a lot of different ways. The book teaches you some different ways. I'm teaching you my way to replace this stuff. I think it's easy and efficient, but here I go. When I start replacing all this stuff, let's think about this. What's that denominator?
U.
That's my u. Let's see, what about this 3? I'm going to pull the 3 out front. So then I got an x squared dx. I'm going to lump that together, and it is multiplied together, although it's written like that. It's x squared dx. I mean, the dx is off to the side, but it can always be considered in the numerator. So it's an x squared dx. So look at this. Here's an x squared dx. So please tell me, what is x squared dx?
1/6 du.
1/6 du. That's how you get it, how you move the 6 over. Thank you very much. So I'm replacing the circled, so look, everything's replaced, right? This is a u, this is a 3. Now what is that circled stuff? 1/6 du. I'll pull the 1/6 out front and put the du right here. By the way, that reduces to a half. And here we go. Can anybody integrate a du over u? Oh, so now you freak out. I see.
Yeah, it's not true.
Right, it's just a memorized form. It's a memorized form. Like the integral of sine u is negative cos u. It's kind of just memorized. Maybe you memorize it because you know the derivative rules kind of good, so you've learned these antiderivative rules kind of good. So this is the integral of 1 over u du. That's one way to think of it. Maybe you don't see it like that. It's a 1 over u du.
Yeah.
And that's the antiderivative. His antiderivative is natural log. Because I remember the derivative of natural log was 1 over x. So the antiderivative of 1 over u is natural log u. So that's it. Oh, let's put u back in there. U is 17 plus 2x cubed. I mean, you do the U substitution so you can fit a form. Okay, you're form fitting these things. This is famous. Once you've done the U substitution and made it look like this, it's log U. Just because you got it memorized, you just know it's log U. The antiderivative of 1 over U is log U.
Would that have worked if you let U be x cubed or 2x cubed? Or would you have to have more steps?
Then you might need a W substitution.
Oh, okay.
So she just asked me, right, would it work if I would have just let this be U? Now, I mean, I want the whole denominator to be U.
That's what you use.
Because I see what I'm shooting for. I'm shooting for a 1 over U du. That's what at the beginning, that's what I kind of see.
Okay.
You know what I never did Friday or last week? I was doing a little of this U substitution. By the way, these natural logs, they come up in 5.7, and you ought to start working there anytime now. It's just more U substitution with natural logs. We skipped 5.6. You can jump from 5.5 to 5.7. There's a lot of good U substitution stuff. But this log comes up a lot in 5.7. And some other stuff I need to get to, but I'm running out of time today. Listen, one thing, this is an awesome integral. This is awesome. And I didn't do any of these last week, but it's U substitution, but it's tricky. It doesn't fall into place. These are all the perfect, nice ones. These are nice U substitutions. This one's not nice, but it's still cool. It'd still be cool and not nice, maybe. All right, you ready? What do you think U should be?
Square root of 3x.
What's inside the square root, I think. Just what's inside the square root, I think. And so then what's du?
3.
A 3 dx. See, what's weird about this, when I start replacing this, now watch this. Watch what happens. There's this x squared out front. And I don't think, there's nothing that's going to really wipe that out. I like when, see, it got wiped out over here. I needed that to get wiped out. This time it's not getting wiped out. It's still there. Or I don't know, there's another way to say it. It got absorbed into the du. It got absorbed into the du. Anyway, that doesn't look like that's happening this time. So this x squared is still there. What's next? The square root of?
U.
That's my u, okay. And then what's out there on the end? What's dx?
1/3 du.
1/3 du. All right, I'll pull the 1/3 out front, and I'll call this du. All right, listen, this is bad. When we do a U substitution, we're supposed to change the whole integral into U's. And all the variables gets changed into U's, and then there's a du there. So, I mean, we're not mixing half with X's, half with U's. I mean, we need to get completely into U's.
Can you make another substitution?
Yeah. So I got this extra X stuff that didn't get replaced, so like this stuff did. So I got this extra X hanging around. How can I get rid of an X? What?
Go back to the U equals 3x minus 4 and get x by itself.
I can solve 4x in terms of U. So this is a more sophisticated U substitution problem. I got to go back. I got to add 4 divided by 3. Are you with me?
Yeah.
U plus 4 divided by 3 is x. I guess I'll have to take x and replace it with that. Holy shit. This x now gets replaced with u plus 4 over 3. It is squared. This is u to the 1/2 du. Yeah.
Yeah.
Now you're ready. Except you got some work to do still.
Yeah.
But at least you got it all out of x's into u's. And sometimes it takes some creative solving to get your problem out of x's and into u's. You saw that? You with me on this? I mean, this is advanced U substitution. This was basic U substitution. This was medium U substitution. This is advanced U substitution. I'm happy if you got with me so far. I'm happy. But you probably want me to finish, don't you?
Yeah.
But I don't care about finishing. I just care. Did you catch it so far? Did you? All right. No, I do care about finishing. What you have to remember is there's no product rules for integrals. You don't just integrate I mean, you have to integrate separate terms. I think in order to finish this problem, you have to FOIL it all out, distribute and FOIL, and then you can integrate. You have to kind of, yeah. You don't integrate products. You can't integrate him and integrate him. There's no rule that, you gotta FOIL it out. You're allowed to integrate separate terms that are added and subtracted together. So I'll finish this, but it takes a little work here. Let's just finish it though. Can I square this 3 and call it a 9? And then pull it out front? Can I pull a 1/9 out front? All right, so then I think I'll have a 1/27 out front. Can I go ahead and square the u plus 4 squared? That's going to be u plus 4 squared. It's going to be u plus 4 times u plus 4. FOIL it out. It's u squared plus 8u plus 16, I think. And then I got this u to the 1/2. So I did quite a bit of algebra from that step to that step. Can you handle it?
Yeah.
I described it orally, but I only wrote down some of it. I squared the binomial. I squared the 3, pulled it out as a 1/9. I squared the binomial. That's what I did. I squared the binomial. I squared the 9 and pulled it out front. Now, I think I would distribute this. That means multiply. That means add exponents. This is u to the 5/2. This is 8u to the 3/2. This is 16u to the 1/2. I think that's what I did. I just added exponents. Guess what? I still haven't integrated. I've done all this work, but now I'm prepared to integrate. I've done all this work, but now I'm prepared to integrate. I've got 3 separate terms. I just integrate each term. Bam, bam, bam. I do power rules. Real quick little power rules. They're nasty little power rules, actually. Add 1 to that, please. U to the 7/2. Multiply by 2/7. Add 1 to that. U to the 5/2. Multiply by 2/5. Don't forget there's an 8 right there. Multiplied 8. Add 1 to this. U to the 3/2. When you add 1, u to the 3/2 times 2/3. Don't forget there's a 16 right there. Multiplied 16. We're done. Plus C. Don't forget another thing. What else did I forget? A 1/27 out front. All right, we're done. Oh, we're done. We're finished is the proper word. You're not done unless you're in the oven. We're finished. Except for one little thing. We're finished. We integrated. We found the nasty big antiderivative.
For you.
Right. I should put my answer back in its original variable. The original variable was x's. Where were they?
3x subtract.
Yeah. All those u's should be represented by what they are. A 3x minus 4. Well, yeah, it's just writing, right? It's just writing. 2/7. 3x minus 4 to the 7/2. What's this? 16/5. Is that okay with you? 3x minus 4 to the 5/2. What's that? 32/3. You guys okay? 3x minus 4 to the 3/2. Keep in mind, you don't have to clean these up. You don't have to factor them. I mean, I'm happy. Now I'm happy. You don't have to make me more happy. I'm happy, very happy.
But to you could be able to factor it out and do all that.
I don't want to, but I don't know. I don't want you to miss the big point. You know, there's a lot of little details. You got to get all the details, but what was the big point?
U-Substitution.
U-Substitution that didn't seem to work out very perfect. And you have these extra x's you got to deal with, and you have to solve for x in terms of u and substitute. Yeah, you have to get creative. I feel like you got to get a little creative with your U-Substitution here.
Why can't you do a little circle thing like you did in the previous one? Why
Well,
is it not working this way?
So, right. So that little circle thing ain't magic, man. That little circle thing is an x squared times dx. Do you see an x squared times dx somewhere in your notes here? Do you see an x squared times dx?
Oh, it's not in the oh, okay. I see.
Yeah, and so what could you do with that x squared dx? You could replace it with a 1/6 du. Okay, I didn't have that over here. I didn't have an x squared dx to circle and replace it with anything. Right. So this x squared was extra stuff I had to deal with, and this is how I had to deal with it. Right, he's right. Listen, this x squared became part of my du. That's the beauty of some U substitutions. This x squared was left hanging out here. I had to deal with it like this. Well, you want to try a nice easy quiz? All right. We got a lot of extra seats nowadays, so I really would like you to spread out. If you've got two or three in a row and sitting next to somebody, please spread out.